So I'm going to talk about tracking data flow in digital brains. All right, there we go. So I evolve brains. That's what I do in my research. And I evolve simple brains to solve simple problems. So here are two examples of the sorts of problems that I try to tackle. This left one is an associative, a very, very simple associative learning task where the agent has to follow a path, but the turn signals are randomized. On the right is a block catching task where there are blocks of different sizes that fall in different directions, and under different conditions, we either say that certain blocks, in this case, the green block should be caught and the red block should be missed. And so these,
yes,
these are not, yeah.
Who knows?
So these agents are not, they're not geniuses, but they are evolving to do tasks. So the way that I think about these brains, this is a very simplified way to think about a brain, is that there is some sort of time t data, which is comprised of inputs and hidden, and it flows through some process, which is sort of like thinking. And then this generates outputs and the update of the hidden or recurrent state. And the recurrent state is just fed back into the brain. So this is sort of a feed forward kind of a process with memory. Oh, well, here's a better picture of it. So we can talk about like an RNN, a very, very simple RNN in this sort of model where the inputs and recurrents are effectively treated the same way. They're all put through threshold nodes, and each output and each recurrent has its own threshold node. Or we can talk about Markov brains, which have inputs and outputs, and their data is fed through genetically determined gates, the output of which determines the output and the hidden. So what I want to be able to do while I'm working on these brains is say something. I can watch movies and I can look at what they're doing, but I'd like to have some more objective measures. And what would be really nice is to have hands-off objective measures of what's going on. And so I've started to look at using information theory as a tool to get me these sorts of statistics. There are already a bunch of information theory neurocorrelates that exist, one of which is phi, which is given, and I'm just giving this as sort of a background. Given some information network, phi measures the complexity of interactions, very loosely speaking. Then there's the idea of representation, which says given a set of salient features of an environment, R asks how much internalized information a brain has about those features. There's another concept called smearing, which asks how spread out or how smeared those representations are within an information network. And then I'm going to be presenting, the work I'm presenting today is really related to this new neurocorrelate fragmentation. And this asks kind of where is the information specifically. So phi and representation and smearing all ask sort of general questions, and fragmentation tries to say, well, yeah, okay, but specifically in the brain, where is this information? Now I'm gonna do a little remedial sort of Shannon entropy. This hopefully will go pretty quick, and there's a payoff, I promise. So information theory, as I'm using, is based on Shannon entropy, which proposes entropy as a measure of uncertainty. Simple systems have low entropy, and complex or random systems have high entropy. Information in this context can be thought of as the ability to predict the behavior of a system. So if you have information about a system, you can predict how the system will behave. If you lack information, the behavior of the system will appear random. And then information theory provides a bunch of different measures. For example, you have entropy, which is just uncertainty. You have mutual entropy or shared entropy, which is information, and this is what A knows about B. And you have conditional entropy, conditional information or mutual information if you discount some information. So what A knows about B if we discount what C knows about B. Don't really worry about conditional information for the purposes of this talk. We're only going to be working with information and entropy and information. So 1 and 2. So how do you calculate entropy? You rely on Shannon, and it's the sum of the probability of each event that happens times the log of the probability of each event that happens. And we're talking log base 2 here because I'm going to be working in bits. And then you have to throw this minus sign in front of it. I'm not going to try to derive this in any way, but I will show you what you can do with it. So let us assume that we have a pattern tilde hash hash hash. And we're given that there are two symbols, tildes and hashes. Then it's -1 times the probability of a tilde times the log of the probability of tilde plus the probability of a hash times the log of the probability of a hash. And that gives us, well, a quarter of the time it's a tilde. So we put quarters in here and here. 3/4 of the time it's a hash. So we put 3/4 in here and here. We run the math and we get back 0.8112. So there is 0.8112 bits of information in this, of entropy in this string. We can look at a pattern like this, tilde hash hash tilde. Again, assuming that there is tildes and hashes as symbols. And what we get out is, oh, well, I need 1 bit to represent this string. So now let's talk about logic with entropy. So here is 0, 1, 1, 0, which is the same as our tilde hash hash hash, or we could talk about, and this is the, if I set up my inputs to a logic gate, an OR gate, 0, 0 through 1, 1, this would be an OR gate. And this would be an AND gate, and this would be an XOR gate. And so we see that the output of an OR gate has 0.811 bits. Same thing for an AND gate, and an XOR gate has 1 bit. Okay, so let's think about this AND gate. Well, this left column has 1 bit of information, because if it's 0, 0, 1, 1, this is the same as 0, 1, 1, 0. It's the same as the XOR, so we know that it has 1 bit. The second column also has 1 bit. The third column has 0.81 bits, so let's put those where they belong. And now we can consider A and X together. And we're going to calculate the shared entropy, or the information between these two variables. And so if A is 0, then we know that X will be 0. If A is 1, then X could be 0 or 1. And so this is, if A is 0, depending on the state of B, well, it doesn't matter. The AND is going to be 0. So if it's 0, it's going to be 0. But if it's 1, we have to then look at B in order to know which one. And so what we end up with is, we end up with these 4 possible states, A being 0 and X being 0, A being 0 and X being 0. That's these 2 lines. A being 1 and X being 0, and A being 1 and X being 0, and X being 1, which is these 2 lines. So half the time we're 0, 0, so half log half plus quarter log quarter for this one, plus quarter log quarter for this one, gets us 1.5. So there is, let's put that where it belongs, there's 1.5 bits on the combined AX system. So, okay, now that we have the 1.5 bits, to get shared entropy, we take the entropy of each element independently, sum them, and we subtract the combined entropy of the 2 pieces. So there's 1 bit of entropy here, there's 0.81 bits here, and then there's 1.5 in the combined system. And so we end up with 0.31 bits, and we can put that where it belongs. And what that tells us is A tells us 0.31 bits about X, or A predicts 31/81 of the state of X, or about 38% of X. So if I know A, I know about 38% of what B's state is. So now we can talk about logic and entropy, and or we're still talking about logic and entropy, but we can talk about, we can draw this up as AND and OR have this kind of a relationship. XOR has this kind of a relationship. The thing I really want to point out here is that there's 1 bit of entropy here, and there's 0.81 bits of entropy here, but this 1 bit of entropy only provides 0.31 bits, or 38% of this state. And if I add these 2 together, I get 0.62 bits of information, which is less than the 0.81. In XOR, it's even worse. If I know this bit, it tells me nothing about the output of the XOR. And so the important thing here is that these states here at the bottom, the outputs of these operators, contain more than the sum of the independent information that we can glean from knowing either of the bits. And this is encryption. And so we can think of the input bit on the left as the data and the input bit on the right as the key. And what we see is that in the case of and or, we have a lossy encryption because we don't get out, right? If we put in this one bit and we have the right key, we don't get out a bit. And in XOR, we have perfect encryption. We put in a bit, we get out a bit as long as we have the right key. All right, so this is just setting up when I'm talking about encryption, this is what I'm going to be talking about. So now, what is fragmentation? So fragmentation is a measure of the minimum number of nodes in an information structure that must be considered to predict some feature. For example, in the AND system, the inputs are the nodes and the result is a feature. And predicting the feature, the AND, requires that I know both nodes. So the fragmentation of this system is 2 because I need to know 2 things. Excuse me. So we can calculate, to calculate fragmentation, we have to define all the partitions of the nodes of a network, which is the power set of all the nodes. And then we start at the smallest partitions and we calculate the shared entropy until we find a sufficient shared entropy or we run out of partitions. We can also create something called the fragmentation matrix, where we don't stop when we find sufficient entropy. We just fill in all of the values, and I'll get to that in a minute. So let's look at an example. I have this question, should I take an umbrella? And I have these 4 pieces of data. So I know the truth value of 2 + 2 = 4. I know whether or not I'm currently hungry. I know if it's cloudy, and I know if it's freezing. Okay, so I can break this down into fragments. Actually, before I talk about that, let's talk about what these mean. The fact that 2 + 2 = 4, whether or not that's true, has no bearing on whether I should take an umbrella. Likewise, whether or not I'm hungry has no bearing on whether I should take an umbrella. Now, if it's cloudy, I maybe should take an umbrella, but I'm not sure. If it's freezing, well, I shouldn't take an umbrella, but if it's not freezing, maybe I should take an umbrella, right? So in fact, it's the case that if it's cloudy and not freezing, it might rain, so I should take an umbrella. But that's the case where I should take an umbrella, cloudy and not freezing. So I can now define all my fragments. Here's the fragments of size 1. Here's the fragments of size 2, size 3, size 4. And now I ask, which is the smallest fragment that will allow me to predict whether or not I should take an umbrella? And it's freezing and cloudy. So fragmentation here is 2. I can extend this by adding an extra piece of information, and that is a weather report. Now, if I have a weather report, I don't have to consider whether it's cloudy or freezing. I could just look at the weather report, and so the fragmentation now drops to 1. All right, so if I extend this into a fragmentation matrix, what I end up with is 2 + 2 tells me nothing about whether I should take an umbrella. Whether or not I'm hungry tells me nothing. Cloudy or freezing each tell me about 38% because this is an and relationship. The weather report tells me 100%. If I was hungry and it's freezing, well, that still only tells me 38% because hungry doesn't change the fact. I mean, I still know that it's freezing, so it's still 38%, and hungry doesn't add anything. And if it's cloudy and freezing, it's 100%. So if I know the weather report, if I consider the weather report, then I could predict whether I should take an umbrella. If I know that it's cloudy and not freezing, then I can predict that I can take an umbrella. If we have an agent and the agent with this information does the right thing, we have a problem, which is we don't know whether or not it looked at the weather report or it looked at cloudy and freezing. So we don't know which of the inputs was responsible for the correct behavior. Okay, so I'm now going to talk about some specific data. I'm going to talk about some tasks. The first task is NBAC, and in NBAC, we feed an input to the brain 1 bit at a time. Every update, we feed 1 bit, and the brain is tasked with outputting the bit that it received on the prior update and the bit from 3 updates ago and from 5 and from 7 and from 8. And so it's a very simple memory task. It just has to hold on to this information for up to 8 outputs and output the correct information. If we look at fragmentation matrices, these are all fragmentation matrices of agents that perform the task perfectly. And we can see in the first 2 that all of the fragments that are needed to predict outputs 1 through 4 are of size 1. In C, we have a fragment of size 2. There's no fragment of size 1 that will predict output 1. And in D, well, it's kind of a mess. We actually have, to get output 4, we have this sort of partial information. And it's not until we get out to this fragment 237 that we actually like have enough information to know this. So in this case, for all the features, the fragmentation on these two is 1. For this one, the fragmentation on these is 1. The fragmentation here is 2. On this one, there's 2 of the outputs have fragmentation 1. 2 of them have, one of them has fragmentation 2, and the other 2 have fragmentation 3. Now, we can take a fragmentation matrix and we can turn this into a data flow plot. And so we can see that in A, we have a very simple data flow plot where input flows into a hidden node. And from that hidden node, it flows to an output and then to another hidden. And then this is the skip, right? So we're going to skip a step here. So this looks pretty much exactly like the schematic that I drew. In B, there is an encryption, but we don't see it in the features because it's happening on these hidden nodes that we don't use. But we can see that there's an encryption here because we can see that I've got 1 bit of information here. There's 100% predictivity of the next node. There's 100% predictivity of the next node, 100% predictivity of the next node, but there's H3 does not predict, provides no information independently about H2. It needs H0. And what's happening here is that there's an encoding happening. There's an XOR happening in H2 between H0 and H3. And then on the next update, the information H0 is now in H4. And so it needs H4 to decode it. And so this is a simple encoding, decoding of an XOR. These other 2 brains get more complicated. And so we can see that 0.6 here is required to get output 1. And if we look at output 1, it's right here, and we can see hidden 0 and hidden 6 are the nodes. But the encryption that's happening in this brain is pretty crazy because there's this feedback, right? There's a 0 coming in here, there's a 0 coming in here. And so there's this feedback loop that's creating some encryption here. And then this brain is even messier. This is just a big mess of, you know, it's just a big mess. I want to really stress the point here that if we look at these brains, this is the simplest solution here. There is no need for the solution to be more complex than A. And yet, when I have all brains, we get all kinds of variety. Now, most brains are like A with some like B, and then D is very rare. But we do see these brains developing. So here's another task. This is the block catch task. I described it before. And here are fragmentation matrices. Now here the features are, should I catch the block? Yes, no. Is the block moving left or right? Is the block size 1, 2, 3, 4? And then these joint ones, should I catch it and is it moving left? Should I miss it? Is it moving left? Should I catch it? Is it moving right? Should I miss it? Is it moving right? And these, what I'm showing here is I'm showing all of the small fragments, and then I'm skipping a bunch, and then I'm showing the really big fragments, just because if I don't skip this, it's too wide to show the data. And here, what we can see is that, well, one, the brain doesn't know that much about what's going on in the world. There's a lot of things. It has very little information. You can see that this is not quite black, but it seems to have very little information about whether or not it should catch the block. In this case, it has quite a bit more. And it really seems to know one thing. In this case, whether it's moving left or right. In this case, whether it should catch it and it's moving left. So, you know, what's going on? So we can look at the data flow in these brains. So this brain here, this is the data flow for the brain. This was actually the simplest in terms of the number of links and the amount of hidden used among the brains that evolved in this in this experiment. And this is looking at, so we can see that there are these 4 inputs which relate to, these 4 sensors, these light blue squares. And those are those 4 inputs. And this agent has to integrate information over time because the block is moving. And we can see that it just uses these 2 hidden. And it's hidden 4 and hidden 6. And we can see that if we look at hidden 4, there's quite a bit of information here. If we look at hidden 6, there's a tiny amount. But if we look at 4 and 6, we can see that there's actually quite a bit in 4 and 6. And so this actually makes quite a bit of sense. Now, this is showing the full lifetime of the agent. I can also look at just the late lifetime. So the last 25% of the agent's lifetime for every block that it has to try to catch. And in that case, what I see is that H4 has a self loop that predicts whether it's a 0 or a 1, and it 100% predicts the outputs. And then it's, okay, well, now this sort of makes sense. So there's some algorithm that happens early on that determines whether or not this agent has to be moving left or right. And once it's made that decision, it doesn't even need to look at the sensors anymore. It just has to keep doing that thing. And so by looking at the information flow, we can see that we can, I don't know exactly what the algorithm is looking at A here, but I do know at the end, I do know what the algorithm is that this brain has determined whether or not it needs to be moving left or right, and it's just going to keep doing that forever. If we look at this more complex brain, we can see that there's a lot more connections. It still has a simpler late lifetime description than the early lifetime description. And I think that's all I want to say about that. So I'm going to, okay, so then I'm going to talk quickly about this path follow task. Essentially, we see similar results. So here's, I'm not going to go into details because I'm running out of time. But here we see the fragmentation matrix, and we can see full lifetime and late lifetime behavior. So again, this agent needs to decide if which it has to learn which turn signal is either left or right. And so it's doing that early life. That requires a more complex brain. On the right here, what we see is the actual schematic of this brain. And then here, what we see is a state-to-state transition diagram. And the reason I brought this up is these are all different views. We can look at the flow diagrams, we can look at the matrices, we can look at the schematics, and they all give us different views. And I have more to say here, but I'm not going to because I'm going to run out of time. So what I do want to point out is I have a paper on archive. I'll give the title of it in a second. And in that paper, I looked at the complexity of block catch brains, and I saw that if I consider the complexity as the number of links in the flow diagrams, and then I look at mutational robustness as compared to complexity, there's a relationship where more complex brains are less mutationally robust. So there should be selection against being complex, and yet it still develops. So I'm going to end by saying one task's encryption is another task's data integration. I'm going to make a statement that I don't think anyone will complain about, which is that I think encryption is rampant in nature. We should pretty much expect to see it everywhere. What this means is if you're looking at something like a gene regulatory network, it's going to be very rare that you find a single gene that controls some trait. It's going to be highly encrypted, and this is why GWAS probably have a lot of trouble finding things. The other thing is that maybe all of this unintentional data integration, which is really what encryption is, allows for new discovery, right? Consider that if you have a very simple agent that really knows how to deal with its current environment and it moves to a new environment, it has no tricks. But if the agent has some messy encryption, then when it goes to the new environment, it may actually already have some special sauce that allows it to perform well in the new environment. And so it may be that the encryption that just is a side effect of evolution is also a bootstrapping mechanism that helps evolution perform better. So thank you for listening. I wanted to thank my collaborators, Victoria, Doug, and Chris, who's given me a lot of advice on this. Also Michigan State University, the ICER Center at Michigan State University and the Beacon Center. And if you're interested in seeing a non-fragmented version of this idea, you should look at my preprint on arXiv. And I will take questions if there are any.
Yes, thank you so much, Clifford, for the great talk, which finished this blog.